Having manually wired our TFT display to our Arduino, we're going to use our Arduino to draw on the display. The principles and steps are the same with any microcontroller. The display can handle up to 18-bit color, but we're only going to use 16-bit color for now, so we can keep the data to 2 bytes. The color is an RGB value with a 565 format. 5 bits for red, 6 bits for green, and 5 bits for blue, like this. We have 2 bytes, or 4 nibbles, or 16 bits. So to display full brightness red, we would have this number, which would be F800 in hex. Full green would be this number, which is 07E0 in hex. Full blue would be, which is 001F in hex. Can you see where I got those numbers from? So let's move on to simple color mixing. Black is easy. That's 0 red, 0 green, 0 blue. So zeros right across the board, giving us 0000 in hex. White is full brightness of red, green, and blue. So ones in every bit. So we get FFFF in hex. You can mix and match colors exactly like we did previously when mixing RGB colors. Mixing full brightness red and full brightness blue gives us magenta. To do that, you'd have all ones in the red bits, all zeros in the green bits, all ones in the blue bits. So you would have F8 1F in hex. You can play around with mixing the colors later on, but one of the first things we do in our sample sketch, downloadable from the download section, is for simplicity, we predefined a bunch of colors, so we can just use colors by name instead of their hard to remember hex codes. So looking at the sketch, you can quickly figure out the setup easily enough for yourself. We just quickly define which pins do what job with the control lines. And we've got the data lines hardwired to port D. So now we just send whatever number we want on the data bus to port D, and then do our business with the control lines, which we just defined. So scrolling down to the setup function, we set up a quick for loop to set up our Arduino's GPIO pins, as all outputs for all of the pins connected to the data bus and the TFT control lines. All of the control lines are active low. So we set all of the control lines high for now. We also have to set up port D, the port D data direction register, as all outputs. So we do that here with this line here. The atmel data direction registers were the opposite of the PIC, a 1 for output and a 0 for input. Now that everything is set up, we have to step through the initialization of the display, just like we did with the TM1638 and even the Hitachi display. We start by simply performing a hard reset on the board. We hold the reset line low and wait 200 milliseconds because the electronics take time to respond. We then set the reset line high, so the board is now active, and again we wait 200 milliseconds for the electronics to respond. You remember we had to put in delays with both the Hitachi driver and the TM1638 boards because the driver chips were slow during reset, right? So it's the exact same thing here. I believe this delay is what was causing problems for quite a few people having issues when trying to use their boards. A lot of people on the internet were talking about the dreaded white screen of death or black screen of death, where their TFT display just wouldn't respond. It was displaying a solid white or solid black screen, and that's it. Well, that was one of the symptoms of not properly resetting the board on startup. Some people found they could fix this by merely inserting a longer delay after the initial hardware reset. Unfortunately, this involved some pretty in-depth monkeying with the libraries that have been passed around, which is why so many people didn't even get past this point. Now, we're not using a library. We're writing our own code. And this is a key function that has to be performed correctly, or else our board simply will not work, or it may work improperly. So moving along after the hard reset, we now have to set up the display. You'll recognize some of these steps as we had to perform them on the Hitachi and TM1638 drivers. The first step we got to do is take the board out of sleep mode. So, looking at the ILI 9341 datasheet, which you should have downloaded from the last lesson, you'll find the command both in the contents and on its own descriptor page. Here it is. Sleep out. So if you are using a different driver and datasheet, this might be going by a different name and may or may not be using the same register address of 11. So jumping to page 101, notice again, this command requires delays after you send it. Now it's only asking for a minimum of 5 milliseconds, but on a microprocessor timescale, that's a long time. And it's important. And I would recommend waiting more than 5 milliseconds. So looking back at our sketch, all we do is load that command, hex 11, onto port D. And because this is an instruction, we hold the register select line low, indicating this is a command, not data. And then we strobe the right line with a low pulse. And we have just issued our first instruction to the driver chip. So don't forget that delay that this particular command required. I went way above and beyond when it needed, putting in a delay of 120 milliseconds instead of 5, just to be safe. All right, we performed a hardware reset and woke up the board from its sleep. The first register we'll set up is the MAD control, or Memory Access Control Register, which controls, the orientation of the screen and lets you reverse the color mode if you want as well. It is a command followed by a byte setting the bits in the register. You can find the bit registers on page 127 and what each of them does. We want all of the bits in the register to be zeros to set everything to normal mode. So looking at our sketch, first we set the RS line low to indicate this is an instruction. Then we load the MAD control command, or hex 36, onto the data lines via port D. We strobe the right line with a low pulse to send the command. The driver is now expecting the data to put into the MAD control register. So we put the RS line high to indicate this is data. Load the bus, the data bus, with hex 00 as we determined, and then strobe the right line with a low pulse. Again, bear in mind that if you have a different driver chip, this command may be a different name or a different hex value. You'll have to figure that out from your datasheet. The next important register we have to set up is the color mode register, because the screen can take 6-bit color, 16-bit color, or 18-bit color. We can see in the index that our color mode command is hex 3A. So heading on over to page 134, we can see what we need to set up for 16-bit color. This color mode requires 2 bytes of data per pixel instead of 3. So we'll use 16-bit mode for now. So as you can see, we need to set up the DPI bits as 101 and the DBI bits as 101 as well. So there's DPI, DBI. The remaining bits are both zeros, so we will have 0, 101, 0, 101, or 5, 5 in hex. So looking back at our sketch, we set the RS line low for a command, load the 3A color mode command onto the bus, strobe the right line with a low, set the RS line for high for the data, load our data of 5, 5 onto the bus, strobe the right line with a low pulse, easy peasy. The third necessary step is, just like before with other displays, that we have to turn the display on. Just like before, the screen defaults to off mode on power up because the screen memory will take random values. By defaulting to off mode when it first gets powered up, you, the programmer of this magnificent device, you have a chance to clear up the screen before you activate it. But, just like before, we're weird. We don't want to clean it up. I want you to see that randomness. So, in the last lesson, when you ran the read register sketch, you got to see what the screen looked like in the default off mode. What did your screen do? Was it completely white? Was it completely black? Now, they usually go completely white so that the end user can see the screen actually has power and is responding when they turn on the device. This avoids confusion caused when they turn on the power, and if the screen stays black, it looks like the device doesn't have power. However, this is another area that the programmers ran into trouble in trying to use these screens. The screen just turns white, and either they didn't understand that they needed to turn the screen on, or they messed up on the initialization. The screen didn't get turned on because probably because they used the wrong command, because the display driver chips got misidentified, either by the programmer or the library they were trying to use. So looking in the index of the data sheet on the 9341, this command is called display on with a hex value of 29. You can see the display off command, and this is the mode by default. Now, there is no data for either of these commands. Sending the command either turns the screen on or off. So going back to our sketch, I don't think I need to tell you what's going on here. There's the hex command 29 for turning the screen on. Okay, that is the absolute bare minimum we need to activate and use the display, and that's all we're going to do for the moment. This way, you can test your display so far and see if you're getting the expected behavior. In the sample sketch, you can see here on line 123, I've got a comment block marked out. Basically, I just commented out this chunk of the sketch so we can run our sketch so far and so we can see if it's all working as expected or not. So don't forget, unplug your connectors from pins 0 and 1. If you forget and try to flash your Uno with the wires still connected, it'll interfere with the USB communication and the IDE will just spit out a bunch of errors. With the wires pulled from pins 0 and 1, go ahead and flash your sketch to the Arduino, and once it's finished, plug in D0 to pin 0 and D1 back into pin 1. Just hit the reset button on your Uno, but watch the screen closely to see what happens. Your screen should change from the default off mode appearance to randomness on the screen. Now, that randomness can take a variety of forms. If it's truly random, it'll look just like static on the screen like this. But because of the manufacturing of the memory, the registers can tend to switch to ones and zeros in like a bit of a pattern. So it might look like this. And if you look real closely, you can see there's a bit of randomness to it, but basically some lines are turning white while others are turning black. And it just has to do with how the transistors were manufactured, which sways whether or not the flip-flops flip or flop. So hopefully your screen changed from the default off mode to on, and you're seeing something on the screen. If you are, then excellent, you are off and running. You are communicating with the board and it is responding to your commands. I did something subtle here, but very important. Actually, it's something I did not do. You'll notice we only set up, what, 3 registers? A lot of people on the internet who wrote sketches or entire libraries for these boards set up dozens and dozens of registers in their initialization of the screens. Now that's fine and all, but every register you set adds to the complexity of your sketch and the possibility that you'll set the wrong register or set a register incorrectly, and your screen either doesn't work or behaves in a very weird way. So I simply took advantage of the default settings after power up and assumed that important settings would default to some usable setting. So, like, you see this bald spot here? Yeah, that's from me ripping my hair out, trying to make these displays work when they wouldn't, and trying to work my way through sample sketches and libraries people had provided, where they sometimes wrote over 100 times to memory and registers. And probably 99% of those registers were for functions they would never use, like tear settings for video. So avoid all that hassle and headache and problems, and just use the default settings as much as possible.